The misunderstood power of photophoresis, how metal sheets could float to the edge of space. Imagine this. A seemingly simple phenomenon, often misunderstood, could revolutionize how we explore the upper reaches of our atmosphere and beyond. Welcome to the fascinating world of photophoresis, a force that can lift objects without any moving parts. But here's where it gets controversial. This isn't just about a curious scientific oddity, it's about pushing the boundaries of what's possible in aerospace engineering. The Crookes radiometer, a familiar face with a hidden secret. Most of us have seen the Crookes radiometer, that quirky little device with spinning vanes that seems to defy gravity. But what's really going on inside this glass bulb? Plenty of people think it's all about radiation pressure, with photons pushing the dark sides of the vanes. But this is a classic case of misinformation. In reality, the key to the radiometer's spin lies in something called photophoresis. Photophoresis in action. Photophoresis is all about temperature differences. When light hits the dark side of the radiometer's vanes, it heats up, while the shiny side stays cooler. Gas molecules that bump into the warm side pick up extra energy and zoom away faster, creating a low-pressure zone. Gas from the cooler side then rushes in to fill the void, and voila! The vanes spin. Now, here's the part most people miss. This effect isn't just a parlor trick. It can be harnessed to lift objects, like thin sheets of metal, into the upper atmosphere. A team of researchers has been tinkering with this idea, and they've come up with some intriguing prototypes. The nano-cardboard revolution. Enter the nano-cardboard, a clever design that takes the principles of photophoresis and amplifies them. Picture two thin, perforated metal sheets, one light, one dark, sandwiched together with tiny pipes connecting the holes. These pipes serve multiple purposes. They link the sheets, insulate them from each other, and provide a path for air to move, generating thrust. But how do you optimize this setup for maximum lift? That's where things get really interesting. The researchers developed a model to test different configurations, tweaking variables like the size of the gap between the sheets, the density of perforations, and the number of connecting pipes. The science behind the lift. The model revealed some surprising trends. For instance, the density of perforations is a delicate balance. Too many holes can increase stress on large sheets in a denser atmosphere, but too few can reduce lift at high elevations. And get this, lift doesn't necessarily increase with surface area. A tiny square millimeter of nano-cardboard can produce over 10 times more lift per surface area than a larger piece. The sweet spot for lift? The mesosphere, that mysterious layer just above the stratosphere, about 50 to 100 kilometers up. It's a tough place to study, too high for balloons, too low for satellites, but perfect for photophoretic lift. From theory to reality. The researchers didn't just stop at models. They built actual nano-cardboard sheets and tested them. Made from chromium, aluminum, and aluminum oxide, these sheets are incredibly light, just a gram for a square meter. When hit with a laser or LED light, they generated measurable force, enough to lift themselves in a sparse atmosphere. But here's the kicker. The researchers want to turn these sheets into atmospheric probes, carrying instruments into the mesosphere. And this is where the real challenges begin. Adding instruments and structural components could negate the lift, and getting the sheets up there without damaging them is another hurdle. The future of photophoretic flight. So, is this the future of atmospheric exploration? Maybe. But there are plenty of obstacles to overcome. And what about Mars? The researchers think this technology could work there too, exploring the red planet's mesosphere. But even if it doesn't pan out, it's a neat bit of physics that challenges our understanding of what's possible. Now, here's a question for you. Do you think photophoresis could revolutionize aerospace engineering? Or is it just a fascinating but impractical curiosity? Let's hear your thoughts in the comments. Do you agree or disagree with the potential of this technology? What other innovative ideas could push the boundaries of atmospheric exploration? Share your insights. and let's spark a conversation.